So anyone would like to give the basic principles of what we covered last time? What are the basic issues we covered?
Sir, we have discussed about the sliding failure, tilting, bearing failure, and coherent gravity methods, and sliding along the base. Methods of MSc1, that is then same.
Okay, that's fine. But then what is specific about that? Anything interesting? What is the main thing which we have done actually? That means what is the basis of our design? Basis means the principle, let us say, which we discussed in the lecture on principles of reinforcement also. So what is it we checked actually?
We have find the critical condition, that is between the reinforcement and soil. Like
So let us look at like this. You're able to see the screen?
yes, sir.
So what we have done is, in principle, the resistance provided by an individual layer of reinforcing elements, this is the main thing we have to avoid, is it not? Should be taken to be the lesser of either the friction resistance of that part of the layer embedded in the fill beyond the potential failure plane. So what is the issue? We assumed a trial wedge initially. At because we are using ranking theory, this is at 45 plus 5 by 2 to the horizontal. Okay. So using the potential failure plane, on the left of it is the fascia. Okay. And so that portion is what we call as active zone, which is moving, trying to move out or translate, trying to rotate with respect to the base or translate in exactly same manner as a regular retaining wall. That means conventional retaining wall. Okay. So now the resistance, the geosynthetic is also embedded in the rest of the portion also. So we are talking of that resistance actually, of that part of the layer embedded in the fill beyond the potential failure plane. That is one thing we have done. In this case, naturally, we are considering the resistance means we are considering the bond resistance. That means we are considering the pull-out resistance. Okay, this is what we have done. And when we do a wedge stability, we also check up also the base resistance. That is modified direct shear kind of test. So that is some separate. And also we have considered the tensile resistance of the layer of elements of the layer or a number of layers when we come to wedge. Okay. So what is tensile resistance equivalent to? Is exactly equivalent to the factored earth pressure of that zone, which the individual geosynthetic is trying to take on. That means, if you are assuming a uniform spacing, let us say assume that the spacing is at 400 millimeters of the geosynthetic. This is assumed by us, let us say designer. And so if we are assuming that regular spacing is at 400 millimeters spacing, that is the vertical spacing between the horizontal elements. So if you consider at the J level, at the jth level actually, number of reinforcement, jth reinforcement level. So what is that now? It is supposed to take care of the earth pressure which is occurring above that up to 200 millimeters at half the spacing, and below that under 200 millimeters under half the spacing. So one, you can say spacing, we are going to do SVJ, we call it actually. Okay, spacing in the vertical direction. That is what is supposed to be the earth pressure coming. So that is going to be translated by the friction onto tension now. So tension is going to be the same thing. So we are going to see that, let us say, whatever we assumed earlier, we assumed given length actually based upon the external stability. And if we find that resistance is not sufficient as per the factor of safety, what it will do? We'll increase the length of it. So the length now is subject to change starting from the external stability criteria. Based upon the individual ones, we are going to probably change the length if required. If the length required is less than what is required, naturally we are not worried about that. It has to be minimum equivalent to the overall stability as per the external conditions. The next of it, next is going to be the tensile resistance. Tensile resistance given by the member itself, by the single layer now. So it will satisfy at each level, right, from top to bottom. That means 1, 2, 3, 4, J, and then to the bottom of 10, 15, whatever it is now. So tensile resistance at a given level is going to be equivalent to the earth pressure, factored earth pressure, of course. All of them are as per factor. So then if this is satisfying individual level now, for the wedges which are going to assume imaginary wedges, trial wedges at different levels, different inclinations, we are going to see that now the number of reinforcements together, if you add up all resistance of each one of them now, so together should be definitely giving us more resistance than what is required. That is what we are trying to do. So the initial friction is coming by the individual level now. The tensile resistance is given by the number of layers or whatever it is now. So these are the two criteria we adopted. This is the fundamental of all our designs. We should not forget that. Okay. Then what else we have considered? Rather, we didn't consider much of it. What is the type of soil actually? Okay, the type of soil we have seen that is most important actually. So in that importance, if you just look at more detail also in development process now, the ranges of soil suitable are also given in the code. That means if this is glacial distribution now, percentage passing, and then particle size. And so this is general range which is going to be suitable for all types. That means both metallic and non-metallic. But if you consider the only the polymeric kind of reinforcement, then we see clearly just for polymeric reinforcement, our consideration is going to be also going to be at up to 0.002. That means one can also, let us say, use a clay material. But then when once you are going to clay soil, what is going to happen now? That is a C5 soil. What is going to happen now? The construction difficulties are going to come up now. Though we can use these soils, but then the maximum size, of course, is almost same. There is no difference in that now. But it only comes to this portion, which we have to consider. And this portion is going to be finer than what is specified here now, because we are extending up to this now. Okay, the bottom line is almost same, but the top line here is higher than this now. So that is allowing the C5 soil. But when it comes to C5 soil, we have to be quite careful on this, particularly for walls. So the C5 soils, as I mentioned earlier, are mostly used actually for slopes, which will be covered subsequently. That is reinforced soil slopes, we are going to use a clay C5 soil. And by and large, in India, we are going to use only granular soils for the fill material. We have no choice on the retained fill because that is a natural soil, and also we have no choice on the foundation also. Now, normally if the soil is stiff, is very good now, we are going to use the entire bearing capacity equation with subject to factoring that now, and in which case it's going to be quite good because we've got a large width now. You know, for a frictional soil now, the width is going to be in a component of the bearing capacity. And because of that now, very rarely the bearing capacity is an issue. But then if the soil is really clayey, foundation soil, I mean clayey, and soft, let us say, or indirectly loose or something like that now, loose sand kind of thing, or medium dense sand kind of thing, then the bearing capacity issue may come up now. Particularly if it's clay soil, probably we have to either go deeper or change the kind of soil by ground improvement methods now. We're not dealing with it now. So by and large, for most cases, for reasonably good foundation soil, this particular structure doesn't need any foundation at all because this structure rests directly on the foundation soil. There's no other intermediate structure now. And also, we know that the fascia is there now. The fascia is going to be usually, we'll go into details much later. In India, let us say, we use 180 millimeter thickness fascia for concrete precast panels now. So that's all what we're going to use. Instead of a regular concrete wall, it's RC wall, we are going to use very thin fascia. So thin fascia is going to be also no foundation, and then the width of the foundation soil also is going to be large, so it's going to be more bearing capacity. We find that these walls are economical. The economy, depending on the site conditions, can vary anywhere between 10 to 15, 20, 30%. And higher is the height of the wall, the economy is going to more and more actually. So a lot of calculation people have done, and you people also can do calculation as you be further going. So that's where the economy is going to be there. Now in this, we also feel that out of the total cost now, the significant cost is coming by the panels or fascia elements now. They are almost 40% cost is only going to panel actually, because the reinforced panel, their connection there and things like this now. So that's an aspect at IIT Gandhi Nagar, we're working upon alternatives and things like this, working out, trying to develop simpler methods of trying to do the connection and also trying to simplify the overall fascia thickness if it is possible. But Indian what you call manuals will say that the minimum thickness is going to be 150 to 180 millimeters. So that is an issue which we have to deal with separately. So these walls are cheap, But also what is going to happen is, sorry, cheap is not correct, but inexpensive. Particularly when in the areas when the sand, good sand is available, that means coarse sand, good frictional property is going to be there. Why? The higher the compaction are going to on a sandy soil, actually, we are going to have obviously more and more phi. If the phi is going to be a 40 degrees, let us say, naturally the earth pressure is going to be less. You know that the more is the friction angle, lesser is going to be earth pressure. So the length of reinforcement required is going to be less and less. And also it helps us to construct. That is, it helps us to construct because we don't have any pore pressures during this now. And in course of time, if by any chance what is going to get into this, get into the structure by some other means, naturally it will drain away very quickly. But in order to drain away from this wall, actually, we have to provide sometimes, we can say, geotextile. Sometimes we provide some pipes and things like this. So all the details I have shown you just quickly in the code, and we also have our own methods in India. The point is that we take care of this in order to see that the water table is not going to go up to the top. Somehow or other, we are trying to see that the structures are considered free of water. Because if you are going to have water in that now, then whatever we are doing, the earth pressure is going to be increasing now. Because if the water is there, in this case, the density is going to increase now. Or otherwise, CPF pressure is going to come up now. So all of them are going to increase the overall cost because the earth pressure is going to increase. And if you imagine that at the top of the wall, the water table is going to be at the top of the wall now. What happens now? Instead of the earth pressure, I assume that the earth pressure coefficient Ka is going to be something like for 30 degrees angle, something like 0.3 or 0.33. Okay. So coefficient is 0.33. If water table is there right at the top of the wall now, we are going to add on another hydrostatic pressure, which means that we are going to add 1 point, another 1 also. Coefficient is going to 1. So the earth pressure which we are going to deal with now, the total pressure, I mean, hydrostatic pressure, coefficient equal to 1, earth pressure coefficient 0.3, so it becomes 1.3. That means, the total earth pressure is going to be almost 3 to 4 times more than what we assumed actually. So obviously, the collapse is going to be imminent. That is something we have to take care of. The other issues which are going to be there is going to be that because of the reason that we are going to use the essentially granular material, the BS code in its figure assumes that the entire wall is like a drain. Basically, there is no effect of water staying there. That is what we have to consider now. So in trying to do this now, that means going back to the first sketch I have shown you in the beginning, we are worried about the friction. Friction we'll talk more probably when we start geogrids now, how to find out the frictional coefficient in terms of the pull-out method. Also by the modified axial, we'll go in details when we start the lectures on geogrids now. So the second and most important point is that how to get the design strength of the material. This I mentioned earlier also, LTDS is what we call. LTDS really means long-term design strength, or we also call it allowable strength very loosely. Allowable strength means naturally there is one value and we have to again factor it in terms of getting the allowable strength. So that is one thing which we are going to discuss today very quickly, because these are mostly kind of descriptive, but there are very important things which one has to consider. And this is what we are going to recap what we have done in the beginning. What did we do in the beginning now? We said there are different ways in which we evaluate the geosynthetics now. One was the physical properties, the second was the engineering properties, the third was obviously construction survivability or installation damage, and fourth is durability. So all of them we have to take into consideration for obtaining the so-called design value. So first of all, we'll evaluate the individual partial factor of safety values for each of the item now. For example, we have got a lot of methods of specifying the materials, like our grab strength or like our trapezoidal tear strength and cone drop and all the things are there. But then for purpose of reinforcement now, there is a separate procedure which is called as installation damage. That means damage during construction, FSID. FS is factor of safety for installation damage, ID. So in this case now, we take a geosynthetic of minimum 9 square meters in full width, the minimum size actually in full width, and it is actually brought to the site basically and placed at the site, and then it is tensioned as though you are using it in the final installation, then backfill using the specified backfill material, and then using this backfilling also first place loosely, then level the whole area, and then of course we use the same thickness as we are going to use loose thickness and then compact it as using the same rollers which are going to use in the actual construction. And what we do now, after applying the number of rolls actually, number of passes, then we first of all remove that after this, and then that is called exhuming actually, and find out the residual strength. So this residual strength is to be as per ASTM some number, and we have to find out the wide width tensile strength test actually. Okay, and the minimum 30 tests are required. This is the basic procedure. So one way of trying to do all this is going to be the factor of safety potential damage is going to be what is the original thickness, original tensile strength divided by the strength which you got now after doing the passing of rollers, passing of number of passes as the actual construction. So then FSID, the factor of safety potential damage is going to be T original by T assumed, and the test obviously has to be as per the code now. There is another way of trying to do. This is ASTM procedure. The British code, in the same code actually, which are saying, also mentions a slightly different one. In this case, 9 bays each of 3.5 meters by 3.5 meters are prepared. 9 bays are prepared, and so the geosynthetic test, which is on one direction 10.5 meters long, is placed without any pretension. Okay, over these now we place 150 millimeter thick layers, 150 millimeter thick layers, or 1.5 times the maximum particle diameter, whichever is greater. Okay, what do you mean by this actually? Why your particle diameter? No, the thickness of construction, that means each roll thickness actually, each lay thickness is controlled also, as I think mentioned yesterday also, by the maximum size of particles which is being the fill material. Supposing the particle size, let us say, the maximum particle size is going to be, say, 75 millimeters now. If you are going to have 150 millimeter thick layers now, naturally, it may be influencing the whole result. So that's why it says we have to use 1.5 times the maximum particle diameter, which is greater fills. Then of 3 different gradings proposed for use are placed and compacted as per practice. Then using 3 levels of compaction, that is standard compaction, let us say 4 passes, over compaction, that means twice the standard compaction, and also double layer compaction. Earlier we thought 150 millimeters, now he says we use actually in 2 layers, this whole thing now. So what we are trying to do, 3 specimens are prepared from each length of reinforcement for visual assessment of damage as well as tensile testing. Thereafter, comparison made with control samples now. So all this is not done for every project, at least by the British code now. In fact, the best thing is that in Britain, whoever is going to use it, and also for other countries now, there is an institution which is called as British Board of Agreement, BBA, British Board of Agreement. Now, the British Board of Agreement is a very interesting development which they have done now. It's not followed in all countries, but then our materials, some of us, our material also are tested by them. What they do now, first of all, when once you apply for a certification, BBA certification, naturally, the group of people, a group of experts are appointed now. This group will consist of some of the user agencies, and then the standard agencies, and then experts. Okay, this group will visit the factory first of all, where is manufactured, and assess for the correctly being done as per the as per the design, as per the process of ISO or whatever it is, manufacturing process. Then they are going to do the testing as specified by the British standards actually. So all the testing is done now, and then they also inspect the sites wherein the construction has gone on now. So once they have done all this now, and they're satisfied with the designs actually, they give you now satisfied with the system. So what they do now, they simply say that this is how we are going to have the panels fabricated. This is how we are going to pick up the soil. This is how the geosynthetic is going to be certified. And finally, what it comes is that it becomes a government material. That means if you are supplying a material as per BBA, naturally it is already pre-tested basically. Okay. So if it's not done only, naturally, we have to apply the default factors. And if you are using default factors, that means, we don't do the testing sometimes, we just apply the factors. And if you see some of the standards now, they are very, very conservative. That means the manufacturer is going to lose a lot actually. So that is one thing we are going to look at. One of the most important things about which we are concerned. The second is the chemical degradation. We are not duly concerned about this unless we are going to have a wall in a landfill area or some chemically strong area. So in this case, 4 geophysics samples measuring approximately 30 by 30 centimeters are immersed in 2 identical immersion tanks of stainless steel kept at 23 degrees Celsius and 50 degrees Celsius using a specified liquid. So as I said, if you are using water, this is not required at all. And if you are using near landfill or near some waste dump or something like that, no. So of course they have to go through maybe EPA is a environmental agency of USA, or by agreement with the client actually, we pick up the specified liquid or specified leachate, and then we keep in the tank actually maintained at one is 23, another 50 degrees Celsius now. And then you start removing these samples at 30 degrees, at 30 days, 60 days, 90 days, 120 days now. And with number of samples now. And one sample from each of the tank is removed, blotted dry of liquid, and cut for test specimens to be used in agreed upon standard geotextile test method. That means, for example, you may say that I'm going to use an narrow strip tensile strength test, or a burst strength test, or a puncture test, whatever we are going to, they said earlier, we just do the test after all the things now. So one thing we are going to check up is why 23 and 50 degrees Celsius. If the data appears well behaved in that no erratic trends are observed, and if the 50 degrees Celsius change is going to be greater or equal to the 20 degrees Celsius change, no problem at all in the same direction. If it is not so, naturally, if it's not increasing appropriately or decreasing appropriately, if there is a variation in this now, then we have to repeat the test anyway. So the factor of safety in this case now obtained as FSCD, chemical degradation, is 1 over 1 minus R50 120 days. That is the 50 degrees Celsius and 120 days actually. Standard reaction ratio of the 50 degrees incubator test at 120 degrees exposure, and that is going to be the factor of safety, partial factor of safety for chemical degradation. The next thing is biodegradation, and we know already that the polymers actually are not subjected to biodegradation, but nevertheless, in rare cases, we may be called upon to not regular walls and things like this. And even if you are using for some purpose a natural fiber geotextile, but that is not for reinforcement anyway. So we shouldn't worry about too much now. But anyway, the client gives us a temperature, site-specific environmental medium under consideration, and there is a guideline for that, ASTM G22, and we take 4 samples of size 30 by 30 centimeters, and then again they are incubated for a number of days now, and one sample from each container is removed after these 6 days and cut for other specimens, and let us say conduct any one of the tests, strip test, burst test, or puncture test. And if no elastic results are found, the damage due to biological degradation, FSBD, is going to be 1 over 1 minus R20. That is, at 120 days result actually is what we are going to do, depending upon what we chose, either the narrow strip or we said burst or puncture. Then we are called upon to the joint strength. Now the joint is not very common. That is, of course, known. Because, if your joint is always weakest portion now, and particularly if you are going to joint in the reinforced direction now, it's not going to be problem. It's going to be a problem. But sometimes we have to do connection of the geosynthetic with respect to the fascia panels now, or wall panels, you can say, or any other system, depending upon what we are trying to construct actually. So sometimes required for us to get the partial factor safety for the joint strength. And in this case, we are going to again use the ASTM right with tensile test now. And in this test, the test is conducted at least 1000 hours now. And with one joint and no joint, we are going to compare the results now. And then naturally, our calculation is going to be FSJNT is equal to T as received. That means the tensile strength as received geotextile divided by the T as joint geotextile. So this is the way in which we do it now. So this particular strength is not always done because we don't come across such joint which is there unless rare cases. And we also seen that biological degradation is also not going to be very common now. So if you try to put in all these things now, what is it we did? We said we got a factor of safety for installation damage. Okay. We got a factor for chemical degradation. We got a factor for biological degradation. And then we got a factor for joints, actually, seams and connections. So what is left out, of course, we'll see the creep portion in more detail. Okay. Anyway, when once we got all the factors as actually tested, and so what we're going to do, we are going to get T allowable actually as T ultimate, the ultimate tensile strength divided by into multiplied by one, in fact divided by all these factors now. Okay, and that is T allowable now. But then the actual strength you are going to use will be obtained as T allowable divided by the factor of safety, which is again called global factor of safety, and this also is mentioned in many cases. Typical ranges between 1.25 to 1.5. So this is actual determined value based upon all the factors now, and then FOS is as upon the depends on the confidence you are going to have on the construction. If you think is a good construction, 1.25. If you think the construction not very much controlled, the factor can be 1.5. So that is why even if we have got, let us say, 100 kilonewton per meter, the ultimate tensile strength now, the allowable tensile strength is always going to be much less, and of course the LTDS, the long-term design strength, is going to be much lower. It could be as small as 40 to 50% of the ultimate tensile strength. So we had to be very, very careful evaluating these values. If you don't do this evaluation, naturally, there is a default factors which will further reduce the allowable values. So we should take caution on that now. So we'll now see the effect of creep. Now this is done, of course, as per ENISO or ASTM. Now main thing is that the tensile creep, that means creep under tension of the geosynthetic now, gives information on the time dependent deformation at constant load. What do you mean with that? If you apply, suppose you take a geosynthetic now, which is pre-tested, apply 100% load, what's going to happen? It will fail instantaneously. If you apply, remain simply fail, it will break it will rupture. Suppose you apply 80% of the load only, ultimate tensile strength. Naturally, it may deform and then may fail. Creep rupture tests give time until failure of the constant load. That means applied 85%, 80% load of the ultimate tensile strength, and naturally the rupture is going to be caused, again failure is going to occur. That time is noted basically. And if you are applying say 40%, 50%, 60% of the tensile strength actually, then we are going to get a creep curve actually. Okay, this creep curve now we'll see in more detail basically. And what we are going to do, we are going to apply the creep by using dead weights and sometimes enlarged by the lever arm, exactly like in a consolidation test. There's not much difference now. So in the case of creep curve actually, we are going to do the deformation measurement. That means we are going to measure the creep deformation. In creep rupture, we are just finding out the time actually which is available. In the case of creep curves, we are going to find out the time versus this one at a given creep load, which is a percentage of the tensile strength of the material. So this is how it's done now. We got the specimens here now. And naturally, we apply low load, higher load, much higher load like this, depending upon what we are trying to do that. And there's a lever arm here also. So all of them is almost like consolidated tests only, except that it is at a given temperature, mind you. Okay, the temperature is monitored continuously. I mean, it's not, oh, it can be plus minus 2 degrees Celsius. No, it can't be like that. But also free from vibrations. Okay, if the external vibration in the structure, naturally, the result is not accepted. And so another way of doing this test, again, we have the just to show that the grips are exactly the same kind of grips which are using in the for measurement of tensile strength. And these are the good old grips, which the Tensor company was using. So I thought I will show you that. And sometimes, the specimen is held horizontally also, no way. And the important thing is that it is a temperature controlled this one, and naturally we keep many samples under test simultaneously, because now if you give many samples, what's going to happen now? The result is going to be quite sufficient. Otherwise, one by one, if you keep doing it, it will take a lot more time. So what do you mean by the tensile long-term strength test actually from creep viewpoint particularly? So is the strength still available at the end of design period and determined in accordance with the NISO number on the basis of extensive testing in creep laboratory? This is a must actually. If the creep results are not available, the geosynthetic can't be used at all. So for which we got simpler methods, quicker methods doing it, but finally the quicker methods have to be re-verified or ratified by actual testing for a given amount of time. That also we'll see. And I will repeat again, there is no default values for this material. That means each time we are going to start a new factory, particularly, each time we are going to start a new product now. If you are going to change the composition of the resin and things like this, naturally, we have to keep doing this repeatedly because this is basis for this now. So what we're trying to say, if our wall is going designed for 120 years now, we should be able to find out what is the strength available at the end of design. How much is available now? So that is what we are going to use in the design. That is why the design tensile strength is always going to be much lower than the ultimate tensile strength. So that is a point which you should keep in mind. The next thing, of course, is that again we got a specimen here now, ready for application of the load now. And on this axis, we are going to plot the deformation. And this is with respect to time now. And what is it we are going to apply some load? Applied on the left hand side, you see the weight. And so immediately there is some deformation. And then we apply this increased load now, further load. And we find that the curve is increased with time. And again, we increase again weight, let us say. And then we get another curve. And finally, apply large load, we find that it is actually becoming like this. So initially, there is a lot of compression. And beyond that, a lot of compression, or I can say tension, I'm sorry, not compression, tension actually. And then, of course, with the time, the same kind of loads, it will be same kind of thing. That is what we have to keep in mind. Okay. So this will be happening with increase in load also, or this will happen also if you just keep the same load for more and more time. Okay. So that is what we have to start looking at it now. Either way it is. So if you now plot versus the life actually, extend this now. If you say that I got 100 years life now, what is going to happen now? Initially when you started the work now, you see this during 2 months of construction, so much creep has already occurred, mostly elastic. And then maybe in 1 year, quite a bit of creep is almost over now. And then for the rest 119 years now, the movement is going to be very, very small and probably negligible. Probably, not always like this. So this is what we have to always keep in mind. What is happening at the end of construction, and then what is happening, let's say, within reasonable time beyond that now, and is it still increasing significantly, or is it almost becoming asymptotic? So this is a typical curve for International Geogrid of the HDPE type. Now to achieve the design goal now, we are going to conduct basically tests, as I said, at different percentage of ultimate tensile strength. So for example, the normal strength in this case is taken as I think 100 kN/meter, and the test temperature in this case is 20 degrees Celsius. And we are going to plot the results with respect to the total strain in percentage, and then also the log of time in hours now. So this is 150 kN/meter now. So we are going to apply 66% of this load. Initially, let us say we applied 30% of the load. Then this is the kind of curve we are getting, the bottommost curve. And keep increasing this from 30% to 40%, 50%, and then 60%. Okay, these are for geotextile and also individual yarn also. So don't get too much confused. So 66% is, let us say, the topmost curve now. So what is happening now? It appears, of course, linear on the semi-log scale. Okay. Now, one more thing I can predict is that if I am applying, let's say, 85%, probably it will be coming something like this, and then it will actually fail completely. That's the rupture, basically. Okay. We are applying near the ultimate tensile strength. Naturally, it is going to immediately some tension, some tensile strain is there, but beyond that, it's going to be simply collapsing. That is the creep rupture. And this is almost coming to that now. So 66% is here now, more steeper line, and at 30% now, it is, I don't say flat, but flatter compared to at higher loads actually. So this is log scale now. And if you see that 100 hours means something like 4 days, is it not? 1000 hours means 40 days. 10,000 hours means 400 days now. So we require 400 days, that means 1 year more or less to conduct this test now. Now we are certifying this for 120 years actually. That means the result for 1 year, we are certifying for 120 years now. So it means really, first we'll say 1:10, one log cycle. That is 1 year to 10 years, one log cycle, and 10 years to 100 years on the log cycle. That means 2 log cycles have been extrapolated. This is the correction we have studied in the BS code also. So we can't do this now. We can at best extrapolate 1 cycle only. That's what we have to see. So that is the difficulty now. So old companies which are 50 years old, 100 years old, they got the data. But what about new companies? That's the problem. So now these same results now I can plot actually in a different way. This is the again the loads we are applying now. Okay, the breaking load versus the elongation, and then time in hours now. So what is it going to happen is we may have the actual test results like this now. Okay, how much percentage you are applying, that is here now. So if you are trying to extrapolate now, how much extrapolation is shown by dotted lines here. That means say 4 into 10 to the power whatever hours, no? Then 6 into something like that we can extrapolate. But can we do so much extrapolation is what we are going to think of it now. So that is the issue which we are going to have, and this of course rupture anyway, ultimate failure now. If you are doing using this initial curves like this now, we can convert them back into a different kind of picture. So from the creep curves to different stress grades, these are called isochronous states, isochronous stress strain curves, and these are extrapolated by using same data. So we have again the stress, which is the ratio of the ultimate tensile strength, and this is strain on this horizontal axis now. Okay. So again, if you are just doing the immediate test now, it is like this, 100%. If you are applying some percentage, it's going to be a different line. So we are replotting the same line now. So first line is going to be ultimate tensile strength now. Second line is going to be 1 hour. Third line is going to be 10 hours, and then finally this is going to be 10,000 hours. That means 400 days basically. So like this now, our results are going to come. If you are plotting the same result in a different direction, actually combining them, that means we are actually seeing the plots in this direction. At let's say 10 hours now, you are going to plot the first point here, second point here, third point here, fourth point here, like this, and then go to the next 100 hours now. So that is simply replotting the data we got now. These are called isochronous curves now. It is giving the time. Isochronous means chrono means the time actually. At the same time, what is the strain which is there? And if you really think that now the creep data for 10,000 hours can be extrapolated out of one order of magnitude, approximately 10 years now. That means one log cycle we can extrapolate. The factor of safety for creep is determined from the 10,000 hour curves as being the load at which the creep curve becomes asymptotic to a constant strain line or 10% less. Okay, if you are using it now, obviously we are using extending to 10 years only. We have to see extend from 1000 also. Anyway, if you're looking at that kind of data now, so we are going to get the same kind of factor now, factor of safety for creep now. Again, the standard value, that is standard design life actually, and then the design life which are getting from this now. So that's the factor we are going to get actually. So that is the value which are going to look at. Now, how we are going to get this now? Very interesting kind of thing. And if you look at the summation of all of them now, what is we are looking for? We are looking at the load in reinforcement. That means percentage of the characteristic strength means the ultimate tensile strength now. And this is the time now. So again, this is of course a log scale only. So what is happening is the creep rupture line which are going to get ultimately is something shown by green curve. That is the real rupture line. Okay. And what did we start with? We start with the initial design value without the rupture kind of, without the creep. So that is here now. So this value, this line actually, we are shifting downward based upon the limiting value of the time now. The margin of safety we are going to get for design life. Suppose design life is say 10 years now. So we are extending this line up to this now. And so that is the design value. That means we are putting it back as a design value. And further, naturally, if you want to extend it to say one more log cycle from 10 years, 100 years, naturally, this is going to be extended and then back to this. Or we are applying a factor of safety here, it will come down like this. So the point we are trying to say is that now we can play with this kind of data and find out now assumed residual strength curve at the failure time, and indirectly, if you know the failure strength, the residual strength now, we are dividing it by the ultimate design strength, ultimate strength as tested, short-term test, and then we get the factor of safety for creep now. So this extrapolation by one order is done at a given temperature. Now, whatever people are very intelligent people, they have been studying the performance of these materials since long. A lot of research has gone into this now. So what they find is that the behavior which are studying now, we are studying at one temperature, second temperature, third temperature now. So they say that now all the behavior actually up till some temperature for each of the polymers now is going to be more or less more or less linear. It's not really more or less linear. That means there is no structural change in the polymer now. So that maximum temperature decided now. So key performance data at an elevated temperature can be used. What we know already is that if you got, suppose we are working in Kanyakumari, the creep temperature is going to be, the temperature is going to be high, ambient temperature. If you are going to Kashmir, the ambient temperature is going to be low. And we know that at low temperatures, the creep is going to be less. At high temperatures, the creep is going to be more now. So using the same thing now, we are going to conduct now at artificially higher temperatures than what is prescribed in the design actually. So that is the elevated temperature we are going to use. And for additional order of magnitude in establishing the time, that means we are going to do, let's say, test at 20 degrees, 30 degrees, 40 degrees, 50 degrees Celsius. And then each range of this increase, 10 degrees Celsius, actually is taken as one log cycle. That means that is called temperature versus the data superposition actually. Okay. So time temperature superposition is what is done. That is accepted in polymer technology. So creep curves from elevated temperature testing may be overlaid upon the creep curves at the desired temperature by shifting the abscissa time scale. That's what we'll see. So the basis of what I explained to you, the time temperature superposition is a fundamental issue which we are taking for granted from the polymer literature, and we are trying to obtain the accelerated creep by using the time temperature superposition now. Is accepted in polymer industry. So what do they say? Higher the temperature, shorter is the testing time. Higher the temperature, greater projection time. But we should increase the temperature such a way up to some limit so that the original polymer structure is not changed. That is something very important for us now. So there is a temperature limit for each polymer, and obviously it is somewhat subjective. It's not always same for everything. It depends on many other things also. So the idea is that we are shifting the short-term data. We are shifting the short-term data. How we are doing shift now? Very interesting. So we got the same kind of equipment which are using for tension testing, except that now the sample which is gripped, in this case of showing grit, it can be any kind of material. This is in a box now. This box actually is like oven. That means in the tension testing machine now, we are putting a box actually. In fact, when we did work at IIT Delhi, we had an instant universal testing machine. It came with a box also. At the time, we didn't know why this can be used. It of course meant for the testing of which was materials, but this can be used very easily. So the box is going to be surrounding the specimen, and then the box is almost like oven only, and that temperature is going to be as per our requirement. We can change it actually. So all these gadgets, all of them are meant for trying to look at that in a proper way. Okay, so then the same kind of result now, let us say it is a HDPE grid, and time is here and strain is here now, and we are applying only 22 kilonewton per meter is the kind of load we are applying, and applying the same load actually, we find that from 10 hours to 1000 hours now, this is a curve at 25 degrees Fahrenheit. Okay, and then the next level curve we are obtaining at 100 degrees Fahrenheit. So then 120, then 140, then 160. We find that increasing the temperature systematically is not increasing the creep curves. I mean, not changing the creep curves exactly kind of parallel, but more or less you can assume that the increase is broadly significant and can be taken as linear in this semi-log scale actually, because this is a in log scale. Okay, so that is the basis for all our work now. So higher temperature, we got another value. So another temperature, another value. So like this, we are going to change it now. So each of this temperature change, we are going to look at as one log cycle. So that is what is done now. So what is it we got earlier? We got this T1 curve. Let us assume that this is time T1, and the initial one is time T1, and then T2, T3, T4 like that. So same thing we are going to use now. So what we are going to do, we have got now log time in hours, okay, and then the log strain, same log cycle, and we started with initially one on the log scale, and so this thing is at room temperature, let us say. This is a curve now. So what is it we are doing now? The next one log cycle actually, we are going to take it as T2. So this T2 curve is merged into this as standard like this. That's why it's shown dotted now. These actual ones. This dot. So we are assuming that actually the temperature is so increased that the effect will be equivalent to one log cycle. One log cycle meant actually if you take 100 hours now, this is equivalent to 1000 hours. Usually it's possible for us to test it also actually and then verify it. And then the next one at T3, much high temperature, we shift it from here by the superposition method from here to here now. So this becomes now say 100 to 1000 to 10,000 and then 10,000 to again kind of 1 lakh. So that is what we are going to do. So we are transposing these things now, superposing these things now, converting them, the effect of high temperature is equal to each temperature increase is going to be equal to 1 log cycle. So that's why we are getting this curve now. Okay, this is what we call as generation of master curve by horizontal shifting. So this is what we call as SIM method, stepped isothermal method. Okay, so this is what we call as accelerated creep by SIM method, accelerated stepped isothermal method. So in the system which is seen, basically, what is it we are going to do? We are going to look at the basic lines actually, and every time we are going to test a new specimen actually. So in one way it is good. It's going to represent the possible product variations. It's not going to vary so much, but it is also possible that product variation is going to be there. And then it's good because it's going to represent all things now. In the stepped isothermal method which we are going to use now, it uses the same specimen. Do you know that actually there's a triaxial method of doing it, estimating the failure value based upon the system curves at higher pressures actually? I think maybe I'll teach you some of the time or ask madam or you've done it now. There's a hyperbolic method of estimating the result. What do they do now? Supposing we conduct the triaxial test at a given confined pressure up to 2% strain only. Okay? So from this now, we can predict what is the failure value by using hyperbolic law. Okay? Now, what is hyperbolic law? Actually, it means that you got a regular symmetric curve kind of thing. And now we got the strain, the compressive strain on the horizontal axis, and we got the vertical stress sigma actually. So sigma divided by again the strain is going to give you the hyperbolic plot in a linear scale now. So when once you get the slope of that curve actually, we can find out what is the ultimate value. That means what is the maximum strength which we are going to get now. So that means at that confined pressure, we are going to get that estimated failure value. Then what we do, we apply higher cell pressure now. So let us say we applied 100 kilopascals earlier, we apply now 100 to 200 kilopascals. Again comes the test up to 2%. So again using that the actual behavior and plot that hyperbolic plot and then estimate what is the kind of failure value at 200 kilopascals confined pressure. Like that we keep doing it now. And the last increment we are going to do, we are going to get the actual value also because that will be subjected to still failure now. So we can verify the linearity of this hyperbolic model, applicability of the hyperbolic model. In fact, we can do for a stress and we can do for a strain, we can do many things. Volume also, we can do it. Anyway, the point is that this particular method uses the same corners hyperbolic concept actually, interactions. And so we are going to use the same specimen now. So what do we mean by this now? We are going to change the temperature continuously. So we got the same kind of equipment now. So using the same temperature, we are going to first do the test actually for a given number of hours. Let's say up to 100 hours now. 1 to 10 to 100 hours now, and then increase the load in the same box. Increase the temperature in the same box now and content. And each of these we are converting back into the strain changes now. So that's how we are going to ultimately obtain the factor which we are considering now. The same sketch we have seen earlier now. So we are going to now, what was missing was a creep. So creep also value has come actually. So all the factors individually are there. And together they are going to give you the factor of safety, partial factor of safety of material now. So divide all these factors, use this as a divisor actually from the ultimate tensile strength and divide it further by a general factor of safety, global factor of safety, and that gives you the long-term design strength. So that is the basis for trying to do all of them. So this is we did all the possible tests now. The initial damage we have done. Chemical degradation we have done, biological degradation we have done, joints we have done. All of them are done actually in a simple way. Creep, of course, is more sophisticated and probably at Jaipur we are trying to install one creep apparatus also now. Probably next month we will be able to do creep testing also in the country. Till now this is not done in the country. Incident damage also we are trying to do. Other things are very simple that we are capable of doing it anyway. But point is that now today we can certify the LTDS now based upon actual testing of the product or products which any company is making. That is required. Then the other point I have mentioned also is about sampling the number of tests now. This picture I've shown you earlier also. Normally we got a production lot or supply lot actually, then lot sample, then laboratory sample and the specimen. I hope you remember all of them now. So in this case, what is it we are going to do is, we are going to look at what are the lot actually. So if you look at the purchaser specification conformance, okay. So if you are going to use a number of units in a lot, that means if you are going to use, let's say 1 to 2, we can select 1 unit. If you are going to use, let us say 65 to 125, we will going to pick up 5 units. That means 5 rolls. If you are going so many rolls, we are going to do this many rolls now. If your rolls are going to be 1000 in a lot, naturally we will pick up 11 of them now. So this pickup of how many units are going to be done for testing is on the manufacturer's quality control, MQC I mentioned. In the same way now, is called assurance. For that now, we want to go to MQA. So beyond that now, we are going to also pick up these things. These are given statistically by the ASTM actually. So the nothing which I am introducing here now. So if you are trying to look at manufacturer quality assurance actually, and then we are going to pick up these things now. So this data should be made available by the manufacturer. So the world manufacturers can view the certified data for this now. For us now, the specification conformance which we are requiring is going to be, if you are going to buy 200 units actually in one single lot, we pick up 1 roll. If you are going to use, let us say 500, anywhere between 500,000 units or 500 rolls, so many rolls, we are going to pick up 3 rolls out of that now. So how many units and how many you are going to pick up actually. So this is how we pick up the number of rolls actually based upon the conformance testing means based upon the quantity of material we are going to. If you think that he is going to get supply the material every time differently from different lots, we have to repeat these things actually. Then we defined also the MAR value. I think I've shown you this earlier. So MAR value is the simplest. What is the MAR actually? Minimum average roll value in most cases, and maximum, of course, in the case of only AOS, apparent opening size. Other case is going to be minimum average roll value. So MAR is simply the smallest or largest anticipated average value that would be obtained for any material tested, and that is originally first time defined by Corner 1994. So this average property value must exceed the minimum value specified for that property based on better test. I will show you, illustrate to you what is the significance of this now. So all this is arranged statistically. So we got a histogram which is giving you so many results which I've got there now, and typical value 180 and then MAR value, all of them we try to see by having a histogram for the purchasers, for the manufacturers quality assurance. You have done one kind of testing now and give you this actually, this entire thing now. So the MQC part of it now is obtained basically, the MAR is going to be equal to the average value or the mean value, sorry, minus the standard deviation, twice the standard deviation now. So that is what we have to, that is what we have to pick up this actually, okay. And if you really require the minimum value now, it will be the mean value minus 3 times the standard deviation. This is basically statistical. So minimum value yields 99.8. You see, before all these things have come now, people are always quoting value 100 km plus minus 5%. What do you mean by plus minus 5%? If it is going to exceed that limit, if our design value is going to exceed the minimum value, we can't do anything at all. So that's why the MAR business has come now. Let us see how to use it now. In a case now, we are trying to prescribe actually, in this case, the quality control in America is GRAB, I told you. So the prescribed value is 700 newtons now. So they prescribed a given quality. Now this is regenerated in India in a different way, but we'll see that also later. So class 2 of the specifications are given now. And for the project now, we are going to require 110 rolls, okay, in one shipment. So geotextile in this case is non-woven with elongation failure specified more than 50%. That is specification. And then results for the samples are presented in the table below. We'll see that now. And the coefficient of variation for the laboratory is undefined. So what is it now? The lot size is 110, we said. That is the number of rolls shipped to the project now. And how many units are going to test now? So from the ASTM code actually, we say that the total number of rolls means we have a lot sample of 5 actually, okay. And so we are going to test how many specimens we are going to test now. Nothing is specified clearly because we are not given the standard deviation by the company. So we are going to pick up 10 specimens for each kind of test. 10 specimens in the mission direction, 10 specimens in the classroom direction now. So this is, let us say, what is tested now. So for number of rolls we picked up already, 5 rolls let us say picked up now. For each of the roll now, we have done 10 tests actually, they have GRAB tests now. So this is individual values now, and this is average value. Okay, and again second row we got this average value, and third this average value, fourth is average value, and then fifth is this average value. So what is it defined for us required as now? 700 value is recommended, 700 newtons is recommended now. So we find that now all these values for each roll are going to be more than this. So we can say that it's good. We should remember that now when we pick up this average value, certain test results are going to be lower also. We are not worried about that. This is included in the finding of the average now. Okay, in some cases exactly same thing now. In some case here is slightly less. So these lower values are not going to be affecting us actually as per the definition of the minimum average roll value. So that is the point we should take into account. So average values should be definitely more than what is specified now. Same thing is done here also in the cosmic direction now. Again, we have values of 700, 704.5, 712, 700.3, 706. So like this now. Again, we find that some values are quite less also, 688, 683. And still there, some values are quite high. So naturally, 700.3 is still higher than what requires 700. So this graph strength of this slot is acceptable. From this test viewpoint, it's acceptable now. Now, what may happen is now, there is a standard value of a way in which we have to do this test actually, and for the laboratory. So another case we are going to pick up now. We pick up another case now. Okay, so we got again all these test specimens tested of all these rolls now, and we are got an average row value, 175, 72, 168, 170, 165. So do we pass it or not now? So that is what we have to see. Now the value which is required actually is 160. Okay, recommended value 160 in this case for as a test. So this is higher, this is higher, this is higher, everything is higher now. So no problem at all. So this particular lot is acceptable now. Now what we find is that if the lowest average value for the test material was below 160 lbs, 160 pounds, that means we'll go back now. If any one of them, supposing this comes to not 160, let us say it comes to 159. Okay, then what we have to do is what is being said. If the lowest average roll value for the tested material was below 160 pounds, it is stated that the lot would be resampled. That means we are going to again do the testing on those 6 rolls, take fresh rolls, and then retest it now. Now, if these are now satisfactory, that means all the individual roll values are more than 160, there's no worry at all. But then, if all the individual average roll values are below the required value, so what do we do now? The entire lot is rejected. Okay, if some of them are lower, we repeat the testing. If all the roll values are going to be less than specified, we have to do this. That's why it is called construction quality assurance. So we are very, very strict in this these days, and that's why the values which are going to look at is going to be that we are not doing one test only. First of all, for each roll, we are going to number of tests in both directions required, and we are also going to do testing for all the specifications also. We are only tested one of them now. We may do narrow strip, we may do narrow, we may do any of them actually. For all of them, it should satisfy the minimum average roll value as per the condition specified. So this is one of the most important aspects of the testing of the geosynthetics now. One, we said the testing is required for finding out the long-term design strength. The second is that we are also going to use the same data for our quality control, both at factory, that's what we call manufacturer assurance, and for the construction quality, because that is where the rolls are tested by sampling, by statistically, as in the STM, and we conduct the test and then certify that the entire lot is going to be this one. So it is not simply picking up any odd roll and doing one simple test, one test of one kind, and say, well, I accepted this now. So this is no way. That means before we buy it now, along with the bid which the manufacturer is going to give to us now, we should see what is that manufacturer's roll values actually, MAR values. And in fact, nowadays, each roll actually sometimes comes, or each lot comes with a certification that this is how the test is done now. One can get more data on this also. So more data means the full stress and curve also is available, and this is how we certify the material is going to be suitable or proper now. So that is the most important thing which is coming out of it now. So as I said, after 2-3 lectures, we'll also go and see how the friction value is going to be determined in the laboratory, because that is another important parameter which is necessary for the satisfactory design and performance of the geosynthetic reinforced soil structures. Okay. The brief name, have you got any doubt?
No doubts.
No doubt. So what is it we are going to get out of this entire thing now?
So main thing is that like how we are applying, like creep is going to happen, and what are the experimental setup for that, and how new comings about the like about the test, creep testing, especially.
So Naeem, what is it you have learned out of this lecture?
Sir, about the different factor of safeties and design strength.
So the last thing I just wanted to reiterate is that one thing is to design the equations and developing an Excel sheet and things like this. That is simpler. Okay. So do things which are responsible for the entire thing other than the loading conditions and things like this are going to be the friction or the interface values actually and the design strength. So unless we know about this now, unless we are doing this work actually, I can just give you, take 1 more minute now. For example, using a coarse grained sand, let us say, and test the construction damage. It's going to cause more damage, is it not, on any kind of geotextile. And if you are using fine grained sand, let us say, it's going to cause less damage. If by any chance you are using silty or clay soil, no damage at all, is it not? So the damage factor we are going to consider is to be for all grain sizes actually, which is allowed in the code. That's why I showed you that entire range of what's the distribution also. So unless we know what is the particle size range generally we are going to use, we can't define the construction damage. The construction damage factors could be given by the contractor, could be given the manufacturer contractor, but you should ensure that that factor is going to come into picture. Otherwise, for example, you're using a polyester kind of material, it will get damaged very easily. If you're using HDB kind of grid, it is not going to damage, isn't it? So the performance is going to be based upon how we're going to evaluate this for the properties which are going to use in design. That means the design is related to this now. That is why it is very much unlike concrete design. In concrete design, when you say it's M25, naturally, there is a way in which you design M25, whether in Kashmir, Kanyakumari, anywhere, north, east, south, west, so you can do the same thing. There's no problem at all. So design, they say that you want M25, khatam hai kahani. Or reinforcement, we can say tar steel bar, we can say that FE 550, whatever it is, we use it now. So FE 550 is going to same throughout the country or maybe throughout the world also. So wherever you go, these material characteristics are going to be remaining same. You choose the material which you want actually. You have to aisa nahi hai. Because we got the same material, let us say 200 kilometer is the basic strength of material. But the design value you are going to use is based on the location. Which part of the country you are going to use it now? Okay, because that gives a temperature. And then what kind of fill material we are going to use it there. And then what is the water which is going to come to structure now. So these are going to be very important for us, more important than the actual design. So design itself is, I should say, simpler affair. So that's why I said conceptually, I tried to explain to you. Now, of course, later when we come to geogrids, our good friend Jimmy Thomas is going to give you again the FHWA Astro method very clearly, but the same fundamentals are going to be there also. Okay, we also need to spend time on the fill. I have just shown you the sketches by the British Code, but we got our IRC, which is based upon essentially the British Code only. Okay, IRC, I think 102 is the manual, and that gives you again the kind of soils and all, and that Dr. Jimmy will tell you more in detail what are the issues comparing the different codes and also what is the choice you have to choose, and if you choose wrongly, naturally again the problem of design is going to be there. Okay, and this failure or this distress is going to be for long term now. You can't repair it so easily because you can't rebuild and you can't remove and rebuild it because traffic is already going over the flyover now. Repair is going to be more expensive. So we have to be quite careful right in design. And after designing now, we ensure that the conditions are going to be in the field exactly as we have used in the design. They are closely interrelated. That is the point I want to make now. Okay. Thank you then.